This is the lecture 3, thermodynamics aspects of intermolecular forces. So, first we will quickly recap the last lecture. So, in the last lecture we discussed the classification of different forces and pair potential, starting from the different way of classification, opposite forces, attractive, repulsive, short range, long range. Then we decided better to classify based on the origin, like electrostatic forces, entropic forces and the quantum mechanical forces. Then we discuss in detail about the strong intermolecular forces, chemical bond and physical bond. Chemical bond we basically consider the covalent interactions, and physical bond we consider the Coulomb's electrostatic interaction between charge, dipole and charge and dipole interactions. We also discussed the van der Waals dispersion force as well as the steric repulsion. Then we combined them and we found that Lennard-Jones potential. Apart from that, we discussed the hydrogen bonds, which is like a ion dipole interactions between hydrogen ions and the electronegative like oxygen ions. Then we also discussed the hydrophobic interaction with the non-polar groups comes into contact with the polar molecules like water, there becomes the hydrophobic interactions. So, in today's class we are going to see thermodynamic aspects of various intermolecular forces, how this pair potential or you can say the self energy is related with the physical and chemical properties. We will also see few examples of this pair potential, how it is related with the solubility, pair potential, how it is related to the electrical potential, and after that in the last we will see how the thermodynamic parameters are calculated, like Gibbs free energy, enthalpy and entropy. So, at the beginning of this lecture I will quickly review the basics of thermodynamics. So, this is I am reviewing the thermodynamics. So, as you know, thermodynamics means thermo energy or heat dynamics transfer. So, it basically deals with the transfer of energy. It may convert from one form to another form, transfer of energy to the heat to the work. The first law of thermodynamics, it talks about the conservation of energy. So, it says total energy of the universe is constant. So, mathematical expression is change in internal energy is equal to dq plus dw. Q is the heat, W is the mechanical work, and dw is defined as minus pdv. P is the pressure, V is the volume here. Now, quickly let us review the second law of thermodynamics. So, it talks about the direction of heat flow. It says that a heat cannot flow from the lower temperature to higher temperature without the absence of some external means, or in other words heat flow from a higher temperature to the lower temperature, and there we derive the term entropy, which is defined as dq upon T. Now, considering here in the first law we are considering the mechanical work, but there can be apart from mechanical other kind of work. So, we will just see du is equal to dq plus dw. So, dw mechanical work minus p into dv, we are adding the interfacial work gamma dA, this is interfacial energy into area. We are also adding the electrical work psi into dq, q is the charge, psi is the electric potential, and as well as the chemical work. So, this can be further simplified dq, you apply the second law of thermodynamics. So, this will be dq is equal to T into delta S. So, it is TdS minus PdV plus gamma into dA plus I into dq plus mu I dNi. So, it says in the thermodynamic terms your work, especially in the first law, whatever work is there, apart from mechanical work, you can have basically this is important interfacial work. So, in the next class we will just see how this surface tension and surface energy are related with the thermodynamics, and of course, this is the chemical potential. So, apart from internal energy, other parameters are there, enthalpy. So, enthalpy talks about the total energy, internal energy plus PV work done. So, enthalpy means the maximum available energy, the total energy. Another parameter is Helmholtz free energy, that is applicable to constant balloon system. A is equal to U internal energy minus Ts unavailable energy. So, this is the maximum available energy in a closed balloon system. Second is the Gibbs free energy, G is equal to H minus Th. H is enthalpy, total energy minus Ts unavailable energy. So, Gibbs free energy is the maximum available energy which can be utilized for the work. So, these are the few review of the thermodynamics starting from first law, second law. This is internal energy, then change in entropy, then different types of work apart from the mechanical work, and here we can relate this internal energy and entropy with enthalpy, Helmholtz free energy and Gibbs free energy. Now, let us go back to the intermolecular forces, or you can see the free energy. So, pair potential between two molecules is defined as C is a constant, R is intermolecular distance to the power n. So, as we discussed in the last class, this is a typical expression of the pair potential, and if you want to calculate the force, force will be the derivative of the pair potential. So, minus dWr upon dr. So, the maximum work that can be done by the force Wr is also referred as the free energy or the available energy. So, Wr is referred as the free energy or the available energy. Now, this is the pair potential when two molecules are interacting, but in actual there will be many body interactions, or you can say indirectly say there will be the effect of medium. So, apart from the two solute molecule or two molecule, they must also interact with the solvent molecule. So, there will be like solute interaction as well as the solute solvent interactions. So, interaction of a particle in a medium is affected by the several factors. The first one is solute interactions. What we are seeing over here is a dissolved solute molecule, it approaches to another solute molecule. If it is approaching means it has to displace the solvent molecules. Now, the net force depends on the attraction between the solute molecule as well as the solute and solvent molecule. So, there are two interactions, and particle may repel each other in the medium if the work done to displace the solvent. It means if the solute solvent interaction is stronger than the solute interaction, then particle may repel to each other. It means there will be no particle or solute interactions. So, you can see this effect of solvent is very strong. So, it can totally change the kind of interactions between the two particles which was there in the free space. This is the first is solute interaction. Next one is the solute solvent interaction. So, if there is a solute, so various molecules of solvent will come and interact with the solute molecule. The solute molecules perturbs the local solvent interactions, and for this the perturbation energy associated depends on the distance between the molecules, and this is referred as the solvation or the structural forces between the particles. So, depending on the distance of these two molecules, there will be the solute interactions. Here you can just see ki this is a solute, it is surrounded by the various solvent molecules. Next is the solvent interactions. So, this affect the property of dissolved molecules such as the what should be its dipole moment, what should be its charge, and as you know this depending on the solvent interactions, or you can say type of solvent, the property of solute changes. A molecule can have different charge on different solvent. So, this comes from the solvent interactions. And next is the cavity energy. So, cavity energy, let us see this example. There is a liquid and another phase gas molecules want to come inside the liquid. So, if you want to introduce a new molecule in the medium, there should be first the formation of this cavity. For the formation of this cavity, this much molecule of solvent must be displaced from this place. So, it involves the solvent interaction to displace, and once this cavity is formed, now this your foreign molecules or the gas molecule will come inside the liquid molecule. So, we can say the introduction of a new molecules in the medium, it causes the cavity formation, and for this cavity formation it utilizes the cavity energy. So, energy required for the formation of cavity for the introduction of new molecule is referred as the cavity energy. So, these are the four many body interactions. First one is the solute interaction, solute solvent interaction, solvent interaction, and the cavity energy. Now, how the self energy and pair potentials are related? So, self energy in very simple term, it is a sum of interactions with all the surrounding molecules. So, pair potential means interaction between two molecules, but the self energy is the sum of interaction with all the surrounding molecules. It includes the change in the energy of solvent due to presence of solute molecules. Now, as you remember, this is the simple pair potential defined as C inversely proportional to the R to the power n. Now, if you want to calculate the self energy, so you have to integrate from the size of particle sigma to the infinite. So, this is the pair potential, this is the density, and this is the volume. 4 pi r square dr is the volume, the density, and this. So, if you integrate, it means we are going to sum it up of all the interaction from distance sigma to the infinite. After integration, it will come out to be 4 pi c rho upon n minus 3 sigma to the power n minus 3. Now, rho, as I told, rho is the number density. So, this the density term you can simply write 1 upon V, and V is 4 by 3 pi, R will be sigma by 2 ka whole cube. So, if you put the value of rho over here, it will be 24 C upon n minus 3 sigma to the power n. So, this you can say how the self energy and how these pair potentials are related. So, if you consider a typical sphere molecules in the medium, it interacts with 12 other molecules, or you can say 12 solvent molecules. So, if you want to introduce a new molecules in the medium, so what it happened? It should displace the 12 solvent molecules. The 12 solvent molecules, it means it must break 6 bonds. It must break 12 divided by 2, 6 bonds. Okay. So, energy required to separate 2 molecules at a distance r is equal to sigma is known as the bond energy, or you can say the we are replacing r with the sigma here. So, bond energy, or you can say the pair potential for the separation of 12 molecules will be 6 into the pair potential, because it is 12 molecules are going to form the 6 pairs. Now, when the new molecules comes, it is again surrounded by the 12 molecules, it is going to form the 12 different interactions. So, 12 new bonds will be formed. So, for this the total bond energy, or you can say the self energy, will be 12 into the pair potential. So, the net energy will be plus 12 minus 6 is equal to 6 into pair potential. So, this is the typical you can say one example which says that self energy, or the bond energy is about 6 times of the pair potential or interaction energy between the two molecules. Now, if you remember what is the value of pair potential in the last slide. So, it was 24 C divided by n minus 3 into sigma to the power n. So, if you take over here, so as it is the half of this, so we just divide by 2 and it will get minus 12 C n minus 3 into sigma to the power n. So, what it says is it is minus C upon sigma to the power n into 12 upon n minus 3. So, what is this? This is your pair potential into this is the number of times how it is related. So, you can say the half of total interaction energy of the molecules is equal to C to the power sigma power n C upon sigma to the power n into 12 into n minus 3. Now, if you remember the last class for van der Waals interactions, value of n was 6. So, if you put the value of n was n is equal to 6 here, so it will be like 4 into C sigma to the power n is equal to 4 into 4 times pair potential. So, this is the typical range. So, here we have taken from the mathematical expressions considering the van der Waals interaction n is equal to 6, we are getting 4 times of the pair potential. Here we have assumed that one spherical molecule is surrounded by the 12 different molecules. So, there will be the loss of 6 pair potential plus formation of 12 pair potential. So, net will be the 6. So, typical value of cohesive energy, or you can say the self energy, is 4 to 6 times of the pair potential. Now, if you want to calculate, this is for one molecule, if you want to calculate for the molar cohesive energy, so you have to multiply with the Avogadro number n0. So, you can multiply, so it will be like 6 n0 into W sigma. So, you can calculate for one molecule, or if you want to calculate for molar, so you have to simply multiply with the Avogadro number. Now, let us consider there are two different interaction energy, that is one is the mu1, other is the mu2 in the two regions. One may be in the solid, one may be in the liquid. As we saw, this self energy or interaction energy is affected by the presence of medium. So, in the two regions, one is having the interaction energy mu1, other is going to have the self energy mu2, and correspondingly the dimensionless concentration is x1 in one region, x2 in other region. So, it is simply related as mu1 plus kT log x1 is equal to mu2 plus kT log x2, both are there in the equilibrium. So, from here we can simply calculate x1 is equal to x2 e to the power mu 1 minus mu 2 upon kT, and this expression is very much known as the Boltzmann distribution. Now, if there are n number of phases, 1, 2, 3, like n number of phases. So, we will write mu I n plus kT log x n is a constant, and this constant is known as the chemical potential. So, the chemical potential, if you just see, is a sum of interaction energy, this is sum of interaction energy plus thermal energy. So, the chemical potential is provides the total free energy per molecules. It is a sum of interaction energy plus contribution associated with its thermal energy. And if you remember the very basic of or the review of thermodynamics, so if you just see here, chemical potential you can define as partial molar function at a constant S, constant B, constant A, constant Q. So, in this way total energy per molecules, or you can say the partial molar energy. The same thing you can write in terms of G, you can write in terms of A, you can write in terms of H as well. So, chemical potential is a partial molar function which is the sum of interaction energy as well as the thermal energy. So, from Boltzmann distribution, you just see we are able to relate the interaction energy with the concentration in different phases, and this can be helpful to predict the physical and chemical properties. So, we will just see how we can calculate the number density. So, here the Boltzmann distribution, let us say you are having the number density which is changing with the distance z. So, this is the initial state mu 0 plus kT log rho 0 initial, alright, z is equal to 0, and if z is equal to z, at the height of z the density is the rho z, and pair potential or interaction energy is the mu z. So, from here we can simply calculate rho z upon rho is equal to e to the power minus delta mu upon kT. So, you can say mu z minus mu 0 upon kT. So, if you are this number density is known to us, we should be able to calculate the interaction potential, or either way if this interaction potential is known to, we should be able to calculate the number density. So, like potential energy, if there is a charge molecules, they are carrying the charge E. So, in this case the charge density, apart from number density, now it will be the charge density rho 2 is equal to rho 1 e to the power. Now, here the potential will be electron into the psi is the electric potential. So, this will be rho 2 is equal to rho 1 e to the power E delta psi upon kT, and this is known as the nearest equation. So, if you see here, what we did is, from the Boltzmann equation you should be able to predict the number density, you should be able to predict the charge density. Now, let us see a quick example here. At what height the density of earth atmosphere half the value at sea level. Okay. So, it says rho 2 upon rho 1 is equal to e to the power minus potential will be m g z upon k t. So, this value is given as the half 1 by 2 e to the power minus m. Now, in the mass of, if you want to calculate the mass of atmosphere, so let us, it is having the air. So, mass of hydrogen is 1.67 into 10 to the power minus 27 kg into molecular weight of air 28, gravitational 9.81, and Z we have to calculate divided by K, Boltzmann constant 1.831 into 10 to the power minus 23 into T is 298. If you solve it, you will get simply the value of Z, which will come out to be about 6 kilometer. So, we will quickly see another example for the potential difference. If you want to calculate the potential difference between the two regions where the charge density is going differ by the factor of 2. So, here again rho 2 upon rho 1 is equal to e to the power minus. Now, here the potential will be in terms of electrical potential. So, E delta sigma upon k T. So, this will be, now the factor of 2, it can be either 1 by 2 or it can be 0.5. So, it can be either 1 by 2 or it can be 2 by 1, because it is not given which direction it is going. So, we will calculate for the both, for the 0.5 as well as for 0.2, e to the power minus electron charge. So, it is already negative, it will be plus 1.602 10 to the power minus 19 into delta psi upon k 1.831 into 10 to the power minus 23 Boltzmann constant into temperature 298. So, from here we can calculate the value of difference in the electrical potential, and if you put the 2, you will get the positive sign. If you get 0.5, it will get negative sign. So, the correct answer will be plus minus 17.8 millivolt. So, these are the very two examples which says that interaction energy or interaction potential can be related with the physical or chemical properties. Now, similarly, one more example is the solubility, as we saw in the very first lecture, how we can calculate the solubility depending on the interaction energy between the molecules. So, this is very simple, the same equation, self energy plus k T ln x 1 is equal to mu 2 in phase 1 k T ln x 2. So, here if you calculate x 2 is equal to x 1 e to the power minus delta mu upon k T. Now, in terms of solubility, this will be excess, but this, as I told in the last slide, this is the dimensionless. So, it will be like, this is a dimensionless concentration. So, it will be like in terms of molar ratio or the volume ratio. Now, let us say if you are talking in one phase, it is a pure solid or liquid. So, x 1 will be 1. So, log of 1 is 0. So, it will be mu 1 is equal to mu 2 plus k T log x 2. So, in this way, if the interaction potential or delta mu is known to us, we should be able to calculate the solubility. If you remember the last lecture. So, we already derived this based on the interaction energy, we calculated the solubility of NaCl. Now, if all three potentials are working together, so we can simply sum. So, delta total self energy will be, it is coming from interaction potential or intermolecular interactions, it is coming from the gravitational forces, it is coming from the electrical charge or electrostatic electrical potential divided by the kT. So, if all three it is potentials are experienced, so we can simply sum them up, and it can be possible if the two different phases are composed of different chemical species. So, it can experience the different, or you can say all three types of chemical potential. So, you have to, what you have to do to simply sum this, sum them up, that is it. Now, what is the strength of intermolecular interaction? Typically, we talk about in terms of kT, the thermal energy. So, if the interaction energy is more than thermal energy, means it is exceeding the randomization effect of thermal energy, or you can say it is winning out the randomizing effect of thermal energy. So, typically if the its value is kT, we call it a strong interaction. If it is less than kT, we call it a weaker interaction. So, let us say at standard atmospheric condition, 1 STP 273 degree Kelvin and 1 atmospheric pressure, 1 mole of gas occupies 22,400 centimeter cube. This is its volume, but if you are going to condense it because of some intermolecular interactions in the liquid phase, its volume is reduces to 20 centimeter cube. Now, let us equate its chemical potential between the gas phase as well as the liquid of the gas as well as the liquid molecules in equilibrium. So, it will write mu I gas plus kT ln x gas divided by mu I liquid plus kT ln x liquid. So, here if you just take mu I gas minus mu I liquid, as you know the chemical potential of liquid is much higher as compared to the gas. So, we can simply neglect this term, we can write minus mu I liquid is equal to kT ln x of the gas and x of the liquid. So, if you calculate the dimensionless volume ratio, so it is coming out to be ln of this is the 7. So, we are going to have the 7 times of the kT mu I liquid, or you can say difference in the chemical potential is the 7 times of the kT. And what it has been observed that this value, if you, it does not significantly change with the temperature in the range of maybe up to 100 to 500 Kelvin. So, if you consider let us say boiling point is falling in this range. So, we can simply write T as a Tb. So, mu I liquid is equal to 7 times of the thermal energy. So, from this expression it says that the boiling point of a liquid is simply proportional to the energy needed to take a molecule from the liquid to the vapor. So, this is the boiling point is directly proportional to the mu I liquid, the energy needed to take a molecule from the liquid into the vapor mu I liquid. Now, if there is a phase change, or you can say the vaporization of one molecules, whenever you want to calculate for 1 mole of molecules, you have to simply multiply with the Avogadro number. So, if you multiply n naught into Boltzmann constant, it is simply the gas constant R. So, now it will be 7 into R Tb if you are talking in terms of 1 mole rather than 1 molecule. Now, if there is a phase change, the energy we call as a latent heat, we call as a latent heat, which is our enthalpy of vaporization or latent heat of vaporization, which is equal to the H is equal to U plus PV, internal energy of vaporization plus P into V. So, if you apply simply the gas law, so PV is equal to R TB. So, you can write R TB here. So, if I rewrite this, so it is coming like L vaporization, latent heat of vaporization is equal to U of vaporization plus R T B. Now, the U of vaporization is already 7 RTB. This is already 7 RTB. So, this is coming out to be 8 RTB. So, here you can simply rewrite like this: L of vaporization divided by the TB boiling point is equal to 8 times of the R. This is equal to R is 8.314. So, it is very close to the 70 joule per mole per degree Kelvin, and this is also known as the Troughton's rule, which says this is a typical ratio of latent heat and boiling temperature. So, from this rule, the if boiling point is known to you, we can calculate the latent heat. If latent heat is known, we can calculate the boiling point. So, typical value is coming like a R 8 into kT. So, typical value is about 9 kT. So, molecule will condense once they are cohesive or the self energy with all other molecules exceeds the value of 9 kT. So, this is a typical value. If the cohesive energy it exceeds the 9 kT, it may condense from one phase to another phase. Now, the cohesive energy, as we know, the cohesive energy you can simply relate with the pair potential, let us say 6 W sigma. So, the pair potential will be, so W sigma and W r will be 9 upon 6 kT, 9 upon 6 kT, or you can say 3 by 2 kT. So, if you want to talk in terms of cohesive energy, it should exceed the value of 9 kT, or if you want to talk in terms of interactions or the pair potential, it should exceed about 3 by 2 kT. So, if the pair interaction energy of two molecules or particle in contact exceeds the value of 3 by 2 kT, it is strong enough to condense them into either liquid or to the solid. So, here what we have seen is the interaction energy, or you can say the self energy or cohesive energy related to the chemical potential, and this cohesive energy or self energy can be used to predict the various physical and chemical property like number density, the charge density, its solubility, as well as even the latent heat, or you can say the boiling point as well. So, these are the few thermodynamic aspects of intermolecular interactions. One more thing, we will just see the effect of entropy. So, in the last class we discussed what is the hydrophobic interaction. So, whenever a non-polar molecules come into the water and its immiscibility is known as the hydrophobic effect. So, typically what happens, there is a hydrophobic molecules, this is IL phase you can say. If it will come to the, there will be the well organized structure of the aqueous phase, or you can say the water. So, this is the typical effect of hydrophobic interactions. Like one example is given here, this is the hydrophobic. It is surrounded by the very much well organized water molecules. well structured the water molecules. So, for this formation of this process, or you can say the interaction of nonpolar with the water molecules, if you just see the thermodynamics of the system, it says that delta G is equal to delta H minus T delta S. So, for this process it is not spontaneous process. So, delta G is greater than 0, but at the same time this interaction is with the nonpolar with the water is the exothermic. So, this value is going to be negative. So, if you want to make this greater than 0, so it means that delta S must be negative, and delta S decreasing a decrease of delta S means the formation of more ordered structure, which is represented here. So, it says water molecules are very well ordered or organized, you can see in this picture as well. So, hydrophobic interaction is basically governed by the decrease in the entropy, or you can say increase in the more ordered structures. So, these are the quick example. Proteins, if you just see the folding of proteins, it always says there is a hydrophobic core surrounded by the hydrophilic shell. So, always the hydrophobic groups are here in the center, hydrophobic group, and at the shell the hydrophilic group. One more example is the lipid bilayer. In the lipid bilayer also what we see is the hydrophobic groups are inside, trapped inside, and hydrophilic groups are placed on the surface. So, this is coming because of the hydrophobic interactions, and which is governed by the decrease in the entropy of the system, because delta G is greater than 0. It is only possible if the delta S is decreasing. If delta S is decreasing, means there is formation of well ordered structure. So, in this lecture we have seen the thermodynamic aspects of intermolecular interactions. We quickly reviewed the very basic of thermodynamics in terms of first law of thermodynamics, second law of thermodynamics. Then we discuss how we can calculate internal energy, enthalpy, and Gibbs free energy, and apart from mechanical work we can include the interfacial work, we can include the electric work, we can also include the chemical works in that term. Then we just see how this pair potential is related with the chemical potential, and then we have seen the individual interaction energy, how it is related with the self energy, or you can say the energy of one molecule interacting with the other molecules. So, which was found to be the you can say the self energy is about 4 to 6 times of the pair potential. Then we saw a few examples how this chemical potential or the self energy can be correlated with the various physical and chemical parameters using very simple Boltzmann distribution. So, we calculated the number density, we calculated the charge density, we also seen the solubility, we also saw the latent heat as well as the boiling point. So, here I conclude this lecture. Thank you very much.